Assalamu alaikum and a very good day to the conference chair, fellow presenters, and participants. I'm Sabrina from UITM Penang, Malaysia. It's my pleasure to share our study, the role of Multisim in developing higher order thinking skills among electronics engineering students. I hope this session will provide useful insights and spark meaningful discussions. In the context of rapid digital transformation, engineering education must adopt approaches that are both effective and aligned with industry requirements. Multisim, as a digital simulation tool, provides an interactive platform that bridges the gap between theoretical knowledge and practical application. This has been shown to improve academic performance, boost motivation, increase confidence, and encourage active engagement in learning. This study examines the impact of Multisim on student learning outcomes and engagement, using pre- and post-test analyses alongside structured classroom observations to provide a comprehensive evaluation of its effectiveness. Problem statement. While digital circuit simulation tools like Multisim have transformed electronics education by enabling interactive, flexible, and cost-effective learning, a persistent gap remains between students' theoretical understanding and their hands-on practical skills. Traditional teaching methods often emphasize cognitive knowledge, offering limited opportunities for experiential learning. As a result, many students struggle to translate theoretical concepts into effective real-world applications. There is a need to explore how simulation-based learning can effectively support both theoretical comprehension and the development of essential practical skills in electronics engineering education. This study demonstrates that simulation-based learning is an effective approach to developing higher-order thinking, problem-solving, critical thinking, and industry-relevant skills in electronics education. It also fosters improved academic performance, heightened motivation, and stronger student engagement. Importantly, the findings reveal that not all students progress at the same pace, underscoring the need for differentiated guidance, targeted interventions, and ongoing performance monitoring to address diverse learning styles and support balanced academic growth. The objectives of this study were to evaluate the effectiveness of simulation-based learning tools, specifically Multisim, in fostering higher-order thinking skills among electronics engineering students. Second, to explore key themes related to students' learning experiences, knowledge development, and perceptions. Finally, to examine changes in students' critical thinking and problem-solving performance. Literature review. Digital tools like Multisim, Proteus, Tinkercad, and LT-Spice enhance electronics education by enabling circuit design and troubleshooting in virtual environments. However, a gap remains between theory and practical skills vital for real-world applications. Simulation-based learning provides a safe, cost-effective, repeatable platform to improve performance and competency. Multisim is widely used, with outputs closely matching lab results. This study examines Multisim-based learning as a means to bridge the theory-practice gap and enhance technical skills, confidence, and motivation in electronics education. The methodology of this study focused on three main aspects. First, for research design and instruments. This study employed a quasi-experimental approach to gain a comprehensive understanding of the impact of simulation-based learning. We used pre- and post-tests to measure students' performance in critical thinking and problem-solving skills within the intermediate-level electronics course. Second, for data collection, we gathered information from multiple cohorts, consisting of 81 student score samples and 50 feedback responses. Finally, for data analysis, all data were normalized to ensure comparability. We performed descriptive analysis to evaluate students' experience, understanding, usefulness, and perceived effectiveness. A paired t-test was conducted to compare pre- and post-test performance, followed by a tier performance analysis to identify patterns of growth and decline. For the quantitative results, this study found that the mean scores increased from 52.76 to 57.71 after the Multisim intervention, indicating improved cognitive engagement and problem-solving skills. Statistical analysis revealed a significant difference, p equals 0.036, p less than 0.05, between the pre- and post-test results, confirming the intervention's positive impact. A Pearson correlation of 0.655 indicates a moderate to strong relationship, aligning with prior research on simulation tools enhancing higher-order thinking in electronics education. Qualitative results. 1. All students reported increased enjoyment in learning electronics. 50% agree, 50% strongly agree, crediting Multisim's interactive simulations, visual learning, hands-on virtual experiments, and instant feedback for boosting engagement, confidence, and overall satisfaction, making the experience more interactive, meaningful, and enjoyable. 2. Over 90% of students reported improved understanding of AC and DC analysis, with similarly high comprehension for gain and waveforms, 84% each, and cutoff frequencies, bandwidth, 82%, reflecting the benefits of Multisim in enhancing concept mastery and practical skills. Moderate outcomes in input, output impedances and frequency response suggest a need for further reinforcement, while distortion showed the lowest positive response, 28%, indicating gaps in instruction or application to real-world contexts. 3. A total of 90% of students agreed, 64%, or strongly agreed, 26%, that they had bridged the gap between theoretical understanding and hands-on practice, while only 10% disagreed. This suggests that tools like Multisim effectively supported the integration of cognitive and psychomotor skills, enabling students to apply theoretical knowledge in practical contexts. 4. 90% of students reported that using simulation tools like Multisim boosted their academic confidence, with minimal disagreement, 10%. This suggests such tools enhance self-efficacy by enabling better visualization, experimentation, and understanding of complex electronics in a safe, interactive environment. For further analysis, tier performance analysis revealed that students showed mixed outcomes from the Multisim intervention, with performance ranging from decline to exceptional improvement. Nearly half benefited greatly, while others made limited progress or declined, highlighting the need for personalized support and ongoing monitoring. Despite overall satisfaction, the study's scope is limited by reliance on a single simulation tool, which may not reflect all learning preferences. In conclusion, the Multisim intervention demonstrated a clear positive effect on students' cognitive skills, reinforcing the role of simulation tools in enhancing higher-order thinking within electronics education. Secondly, it enriched the learning experience by boosting enjoyment, engagement, and academic confidence, while effectively bridging the gap between theory and practice. By fostering both cognitive and psychomotor skills, Multisim proved to be a valuable pedagogical resource in strengthening understanding, application, and overall performance. Finally, while Multisim greatly benefited many students, the varied performance outcomes highlight the need for targeted support and the integration of diverse learning tools. That brings me to the end of my presentation. Thank you for your attention.